in the last lecture we were solving the problem of unidirectional transport into an infinite medium. Okay. We had a surface at z is equal to 0 extending into an infinite fluid, okay, in the z direction. Temperature was equal to T infinity far from the surface, and temperature was also equal to T infinity at the surface at time t equal to 0. Okay. So, and the temperature of the surface T is equal to T1 for when time is greater than 0. Okay. So, those were the conditions at the surface. Okay. So, basically at time t is equal to 0, you instantaneously increase the temperature of the surface to a new temperature T1, and then we want to know how the temperature varies in the medium due to heat conduction from the surface. We will assume that there is no variation. Okay, so, we will assume that there is no variation in the x direction. Okay, so, there is variation only in the z direction, and the surface is at z is equal to 0. So, the first thing we did scale temperature T star is equal to T minus T infinity by T naught minus T infinity. I am sorry, I had used T naught in the last lecture for this surface. Okay. Okay. So, therefore, expressed in terms of T star, the bottom surface is T star equals 1, because T is equal to T naught, therefore, T naught minus T infinity by T naught minus T infinity is 1, and this is T star is equal to 0, okay, at the surface. Okay. We found that there was no way to scale the z coordinates. Okay. So, because the temperature equation was partial T by partial T is equal to alpha d square T by dz square, okay. And there was no way for us to scale the z coordinate, and therefore, we had written a similarity variable psi is equal to z by root alpha t. Okay. This was the similarity variable. Okay. Expressed in terms of the similarity variable, we had actually written the derivatives of T star with respect to time and with respect to z in terms of the derivatives with respect to psi using differentiation by chain rule, and based upon that we had derived an equation for the temperature field partial psi minus psi by 2 dt star by d psi is equal to d square T star by d psi square. This was what we had got by differentiating by chain rule, expressing dt by dz in terms of dt by d psi, and the partial derivative with respect to t also in terms of the partial derivative with respect to psi. Okay. And we had also got two boundary conditions, right, at z star at psi is equal to 0, T star is equal to 1 I am sorry. Okay. And then for psi going to infinity, T star is equal to 0. We saw that the condition as z goes to infinity and the initial condition at t equal to 0 both reduce to the same condition. Okay. So, we have a second order differential equation and two boundary conditions, and we can solve this, okay, to get a solution, okay, where the solution ended up being of the form T star is equal to 1 minus error function of psi by 2, where the error function was defined as error function of some variable x is equal to 2 by root pi integral 0 to x dx prime e power minus x prime square. Okay. And if you plot the error function, okay, you get something that okay, x versus error function of x, okay, you get something that increases and then reaches a constant. This constant value is equal to 1 in the limit as x goes to infinity. In fact, this coefficient 2 by root pi is present specifically so that the error function goes to 1 as x goes to infinity. Okay. So, this was the solution. We had also had a solution for dt star by d psi, okay, which was equal to I think it was C1 is equal to 1 by root pi e power minus psi square by 4. Okay. So, that was the solution for the temperature gradient. Okay. C1 was equal to 1 minus 1 by root pi. So, it should be minus 1 by root pi. Okay. So, these were the solutions for the temperature gradient and for the temperature field. Okay. And from this we had calculated what will be the heat flux. Okay. The heat flux was given by Qz is equal to minus K partial T by partial Z. Okay. Expressed back in terms of the scale temperature and the similarity variable, minus K into T naught minus T infinity by root alpha T partial T star by partial psi. At the surface itself, at z is equal to 0, the heat flux is Qz at z is equal to 0 is equal to minus K into T naught minus T infinity by root alpha T partial. This should be a total derivative because T star is now only a function of psi. Okay. At psi equal to 0. Okay. I can write, so this dt star by d psi at psi equal to 0 is minus 1 by square root of pi. So, I just get minus K into T naught minus T infinity by root of pi alpha T. So, this is the solution for the temperature field and the heat flux, the scale temperature field and the heat flux at the surface. Now, I would like to discuss something about the physical significance of this approximation. Okay. So, this was at z is equal to 0, this was the z coordinate. Okay. Okay. T star is equal to 1 and T star is equal to 0 as z goes to infinity. Okay. And then I defined the temperature in terms of psi. T star is equal to 1 minus error function of minus of okay. Written in terms of original variables, this is T minus T infinity by T naught minus T infinity 1 minus error function of z by 2 root alpha T. Okay. So, this is the solution. Now, what does the solution state? Okay. So, what it says is that you can see that this temperature field depends only upon psi, where psi is z by root alpha T. Okay. So, therefore, initially when T is small, this temperature field will decrease. Okay. So, T is 1 here, okay, T star is equal to 1. At initial time you just have a temperature field that looks like this. Okay. T star is 1 at z is equal to 0 and it is 0 everywhere else. Okay. As time progresses, because of heat conduction, the temperature field will go something like this. Okay. So, as time progresses it will go in this direction. Okay. As more and more heat is conducted upwards, the temperature field will increase close to the surface, but still far from the surface it will decrease to 0. Okay. So, that is what is meant by the temperature field. However, when expressed in terms of psi, it is the same at all time. Okay. When expressed in terms of psi, it is the same at all time. That is, if I take the temperature field, okay, at two different values of z and t, in such a way that psi is the same between those two, that is z by root alpha t is the same or z by root t is the same. In that case, the temperature will be the same. Okay. So, that is what is meant by the similarity solution. If you keep psi a constant, you can vary z and t in such a way that psi is a constant, then the temperature field is the same. Note also this length scale root alpha t that is appearing here. Okay. So, in the limit as z by root alpha t goes to infinity, the temperature goes to a constant value, goes to 0. Okay. As z by root alpha t goes to infinity, okay, then the temperature goes to 0. Okay. So, as shown over here. Okay. So, there is, as this variable psi goes to infinity, the temperature goes to 0. That means that this temperature is different from 0 only in the region where z is comparable to root of alpha t. Okay. The temperature is different from 0, scale temperature is different from 0 only in the region where z is comparable to root alpha t. Okay. Therefore, this root of alpha t is equivalent to a penetration depth. Root of alpha t, okay, for the temperature field. Okay. At very initial times when t is very small, that penetration depth is small because the heating has just started at the surface. As t progresses and as t becomes larger, the depth of penetration of the temperature due to the temperature disturbance at the base, the depth of penetration keeps increasing. It increases proportional to square root of alpha t. Okay. So, since the depth of penetration increases proportional to square root of alpha t, okay, so this is the penetration depth. Okay. Since the depth of penetration increases proportional to square root of alpha t, the gradient decreases as 1 over root alpha t. Okay. The gradient is equal to the temperature difference divided by the depth of penetration. So, as the depth of penetration increases proportional to square root of alpha t, the gradient decreases as 1 over square root of alpha t. Okay. So, that is the reason that you have in this expression for the heat flux is decreasing as square root of 1 over square root of alpha t as time increases. At very initial time, there is a sharp gradient, penetration depth is very small, there is a sharp gradient, okay, as shown over here. Okay. As time progresses, the penetration depth increases, the gradient becomes smaller, heat flux becomes smaller. Okay. It goes as 1 over square root of alpha t. Okay. Since this root alpha t is the penetration depth, okay, so the approximation I have made here while calculating the temperature field is that the temperature is equal to 0 far from the surface, okay, at infinity. Okay. Temperature is equal to 0 far from the surface as z goes to infinity, more specifically as psi goes to infinity, okay, that is z by root alpha t goes to infinity. What if I had a fluid of finite depth? Okay. What if I had a fluid of finite depth? Okay. In that case, okay, let us say that finite depth was h, okay, and I was heating from the bottom at t is equal to 0. Okay. The temperature field can still be given by the similarity solution provided the penetration depth, okay, provided the penetration depth is much smaller than the height of the fluid. Okay. If the penetration depth is much smaller than the height of the fluid temperature effectively decreases to 0 over a distance that is much smaller than the height of the fluid. Okay. Therefore, I can approximate the boundary condition as temperature going to 0 as z going to infinity. Okay. Therefore, the similarity solution will still be valid in that case in the limit as the penetration depth is much smaller than the height of the fluid. Okay. That is very early times because the penetration depth goes as square root of alpha t. At very early times when the penetration depth is much smaller than the height of the fluid, I can still approximate the problem as diffusion into an infinite medium. Okay. So, therefore, so long as h the penetration depth which is root of alpha t is much smaller than h, I can still approximate it as diffusion into an infinite medium, and I can still use the similarity solution. Of course, at very late times when h root alpha t is comparable to h, then you will see that it penetrates all the way to the top, all the way to the height h. Okay. In that case, I cannot use the similarity solution, because specifying the boundary condition as psi goes to infinity or z goes to infinity is no longer valid at this height h, because h is comparable to root alpha t. Okay. So, at very early times during conduction, this similarity solution can still be used even in a medium of finite thickness, provided the thickness is much larger than the penetration depth root alpha t. Okay. So, that is one important approximation that can be made at very early times for conduction. Okay. So, this seems like an idealized problem, okay, diffusion into an infinite medium. Okay. However, it can be used. So, in this case time is a variable. Okay. So, I am calculating the depth of penetration as a function of time. Okay. This can, however, be used for problems where the concentration varies with position as well. Okay. And I will give you an example of that. Steady diffusion into a falling film. Okay. So, I have a surface, a wall, okay, and I have a fluid film that is coming down this wall. Okay. And at, okay, so I will take the coordinate z in this direction across the film, I will take the coordinate z in this direction and x in this direction along the film. Okay. At the location, okay, at the location x is equal to 0, okay, this film is brought into contact with a gas, okay, with a solute of concentration C. Okay. This film is brought into contact with a gas whose concentration is C. Okay. The saturation concentration in the liquid, that is at equilibrium with the gas concentration, I will call as Cs. Okay. The saturation concentration in the liquid at the surface which is in contact with the gas, I will refer to as Cs. Okay. And what we would like to know is how much gas gets dissolved as the film goes down. Okay. Now, if you have a film that is going down, right, and if the penetration depth is small compared to the total height of the film, okay, if the penetration depth is small compared to the total height of the film, I will come back and tell you under what conditions that approximation is valid. But if the total depth is comparable to the height of the film, that means that the penetration of this concentration field is only within a thin region close to the surface. Okay. The penetration of this is only within a thin region close to the surface. Note that this is a liquid gas interface. Okay. So, I have a liquid here and I have a gas here. Okay. So, this is a liquid gas interface. Okay. And for the flow of a Newtonian fluid down a liquid gas interface, the velocity profile is a parabolic profile. Okay. The velocity profile here is a parabolic profile. It has 0 velocity at the wall itself, because there has to be a no slip condition. At the free surface there is no shear stress, therefore, the velocity gradient is 0. Okay. So, therefore, near this free surface, okay, near this free surface, in the region where the gas is diffusing in, okay, in the region where this gas is diffusing in, I have the concentration C is equal to Cs, and you have a velocity field that is nearly a constant, okay, nearly a constant, because near the surface the gradient is equal to 0. Okay. Near the surface the gradient of the velocity is equal to 0, therefore, the velocity field is nearly a constant at this surface. This maximum velocity at the surface, okay, so I will not go into the details here, but it is quite easy to calculate. this maximum velocity at the surface, okay, this maximum velocity which I will call V max, is equal to 3 by 2 times the average velocity, okay, the total height average velocity. So, the maximum velocity is equal to 3 by 2 times the total height average velocity, okay. And this region is moving downwards due to this maximum velocity, and we will assume that velocity is equal to V max within this region where the concentration has penetrated into the film, and C is equal to 0 near the, okay, within the rest of the film. Okay. So, how do we solve this problem? Okay. As this film is moving downwards, you have a parcel of fluid that is moving downwards with velocity given by this V max. Okay. The time of contact of this parcel of fluid with the gas, okay, the time of contact has to be equal to the distance travelled divided by the velocity. Okay, the time of contact has to be equal to the distance travelled divided by the velocity, and the velocity in this case is 3 by 2 V average. Okay. Okay, so as it is going down at a position x, at a streamwise position x, the total time of contact of the film has been equal to x divided by the maximum velocity. That maximum velocity is equal to 3/2 of the mean velocity. So, you can see that this problem, the equation is for the concentration field is partial C by partial T is equal to d partial square C by partial Z square. Okay. In this case, C varies between Cs and 0, which means that I can write that C star is equal to C by Cs. Okay. Partial C star by partial T is equal to d partial square C star by partial Z square. Okay. And this is diffusion into an infinite medium in this case. Okay. The boundary conditions. Okay. So, in this particular case the boundary conditions are okay. Note that this is the z direction, the z direction is into the film, okay, or that C star is equal to 1 at z is equal to 0. C star is equal to 0 as z goes to infinity, because we are considering an approximation where the penetration depth is much smaller than the height of the film. We are considering an approximation where the penetration depth is much smaller than the height of the film. Okay. Therefore, C star has to go to 0 as z goes to infinity. Okay. And at the entrance of the film, okay, at the point where contact starts, okay, so contact starts at x is equal to 0, okay, contact starts at x equal to 0. Okay. At the point of where contact starts, there has been no diffusion yet. That means that C star is equal to 0 at x is equal to 0 for z greater than 0. Okay. And my equation is given by this one. This is the equation. Okay. If I identify t is equal to, okay, the time of contact, okay, is equal to this is equal to t. Okay, if I identify this as the time of contact x by root, okay, then my equation becomes, okay, 3 by 2 V average partial C star by partial x is equal to d partial square C star by partial Z square. I just done this identification and I have assumed that the V average is a constant. Okay, I have assumed that V average is a constant, as it should be in the region where you have a maximum velocity. Okay, where you have a maximum velocity of the film, the velocity is approximately equal to V max. Okay, so that V max is equal to 3 by 2 V average. Okay, so I just get partial C star by partial z is equal to d by 3 by 2 V average partial square C star by partial z square. I should the left side it is x. Okay. So, this is the diffusion equation. It is exactly the same as the equation we had for the temperature field for unsteady diffusion, except that I have this term instead of the diffusion coefficient and x in terms of z. Okay. And I can do the exact same calculation, define psi is equal to z by root of d into x by 3 by 2 V average. Okay. It is equal to z by root of 2 d x by 3 V average. Okay. And then I will get the equation partial C star by partial psi is equal to minus psi by 2 is equal to d square. I should put total derivatives here. Okay. Do the same calculation. Okay. Minus psi by 2 d C star by d psi is equal to d square C star by d psi square. In terms of this psi, instead of alpha t, it has alpha d into 2x by 3 V average, which is the time of contact at that surface. Okay. And my equation for the flux, okay, is the same as I had for the temperature field, except instead of T I have to use x by 3 by 2 V average, and you can easily do that d Cs, okay, by root of 2 d x by 3 V average into d C star by d psi at psi is equal to 0, which is equal to minus okay, and this thing is equal to okay, this is the same as the temperature gradient 1 by root pi, okay, that we had for the previous problem. Okay. This becomes d Cs into root of 3 V average by 2 pi d x. Okay. So, just by analogy, okay, only thing you do is interchange time to x distance divided by the maximum velocity. Maximum velocity is 3 by 2 times the mean velocity, average velocity. Okay. So, just by analogy you get the expression for the flux in this case. So, this is a spatially varying problem. Coordinates are x and z, it is not t and z, it is x and z, but still by the analogy that you identify the residence time, the time of contact as x by root of x by the velocity, I just get straight away what is the expression for the flux. Okay. So, this is the flux at a particular x location. Okay. This is the flux at a particular x location. If I had a section of contact which was total length L, okay, and I wanted to know what is the total transfer rate. Okay. If I had a total section of length L and if I wanted to know what is the total transfer rate, right, then the total transfer rate, okay, will be equal to okay. So, this film, okay, so there is z and x, the length of the film is x in the x direction, you have a perpendicular direction y, okay, across the film and of some width say. Okay. So, this has to be the total transfer rate has to be equal to w times integral 0 to I am sorry. So, rather than the total transfer rate I will just define the average transfer rate. Okay. Note that this flux is the flux at z is equal to 0 at a particular location x. Okay. if I wanted to calculate the average flux, okay, flux over the entire film, right, I have to take the average over all values of x, that is I will get this as 1 over L integral 0 to L dx times j z at z is equal to 0 at a particular value of x. Okay. 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 So, this becomes into x power minus half. Okay. So, this is d C s by L into 2 into L power half. Okay. X power minus half becomes x power half by half. Okay. And this can be written as root of 6 by pi, okay, d C s by L times P E L power half, where the Peckley number based upon the length is equal to V average L by T. So, this is the average flux J average, okay, over the entire length. Okay. And the Sherwood number correlation is written for the flux. Okay. The Sherwood number is defined as the average flux by d C s by L, okay, which is equal to root of 6 by pi into P E L per half. Okay, so, that is the Sherwood number correlation for this particular case. Okay. Calculated the local flux at a particular location x, integrated that to find the average flux, okay, and then used this expression for the Sherwood number to get a relationship between the Sherwood number and the Peckley number for this particular case of contacting of a liquid film. Okay. I will complete a little bit more about this before we go on to the second problem of diffusion into an infinite film. I will continue this in the next lecture. I will see you then.